Hi everyone, I am Dr.N.PRABHA, Associate Professor of Chemistry, A.D.M. College for Women, NAGAPATTINam. Today I am going to discuss about chemical bonding. In previous modules, we know about the definition of chemical bonding, types of chemical bonding, ionic bond, calculate of the lattice energy, and also in the second module, I discussed about the covalent bond and the theories of covalent bond, that means VSEPR theory, VBT theory, and hybridization, types of hybridization. Today, we see about chemical bonding 3. In this module, I discussed about the molecular orbital theory and its application. First, we know what is meant by molecular orbital theory. Molecular orbital theory is a fundamental concept in quantum chemistry that explains the bonding structure and properties of a molecule. This theory treats electrons as delocalization over the entire molecule. When two atoms approach each other, their atomic orbitals combine to form molecular orbitals. For this purpose, we apply the principles of linear combination of atomic orbitals, that is LCAO. In a diatomic molecule, the wave function for an electron in the field of two nuclei, that is A and B, will be given the two modes of combination, that is symmetric and antisymmetric. So we have the equation Ys is equal to Ya plus Yb. That is the first equation. That is for a symmetric combination equation. And the another one is antisymmetric combination equation. Ya is equal to small a is equal to Ya minus Yb. That means that is in the symmetric, the combination summation of the two nuclei, and the antisymmetric, the difference in the two nuclei. The probability of finding an electron in the molecular orbital by linear combination atomic orbital according to the equation 1 is greater than that in either of Ya or Yb. In other words, the molecular orbital represented by Ys has lower energy than Ya or Yb. This orbital therefore leads to the formation of a stable chemical bond. So, this orbital is called bonding orbital. The probability of finding an electron in the molecular orbital by linear combination atomic orbital according to equation 2 is less than that in either Ya or Yb. In other words, molecular orbital represented by antisymmetrical combination as Ya has higher energy than Ya and Yb, that's the two nuclei of A and B. This orbital therefore cannot lead to the formation of a stable chemical bond. So, this orbital is called anti-bonding orbital. The formation of bonding molecular orbitals and anti-bonding molecular orbitals from two atomic orbitals Ya and Yb are shown in the figure. Thus, we find two atomic orbitals combined to give two molecular orbitals, one of which is bonding and another is anti-bonding. When the two atomic orbitals overlap in a linear fusion, we get two molecular orbitals. They are termed as sigma and sigma star. Sigma is for bonding and sigma star for the anti-bonding representation. The overlapping atomic orbitals may be pure or hybridized. Thus, we can have overlapping of SS orbital, PP orbital, sp3, s orbital, and sp3, 2s orbital, sp and s orbitals overlapping, etc. Each such overlap would give one sigma and one sigma star orbitals. When the two atomic orbitals overlap in a sidewise fashion, we get two molecular orbitals. They are termed as pi and pi star bonding. pi and pi star for the bonding and anti-bonding representation. This we can have pi overlap, that is the laterally overlap. This gives pi and pi star orbital. Now let us see what are the difference between the bonding molecular orbital and anti-bonding molecular orbital. In the bonding molecular orbital means that the formed by the combination electrons waving a same sign, that is by addition overlap of atomic orbital. Bonding molecular orbital possess lower energy than the atomic orbitals from which it is formed. The electron density in between the nuclei is high. So, the attraction between the nuclei is also high. This explains the formation of a bond between the atoms. In the anti-bonding orbitals formed in the combination of electron waves in the opposite side, that means by the subtraction overlap of the atomic orbitals. Anti-bonding orbitals possess higher energy than the atomic orbital from which it is formed. The electron density in between the nuclei is low. So, the repulsion between the nuclei is high. This explains the non-formation of a bond between the atoms. Now, let us know the new term bond order in the molecular orbital theory. Bond order means that indicates the strength and stability of a bond. The formula for a bond order is equal to half Nb minus Na. Nb is the number of electrons in a bonding molecular orbital. Na is the number of electrons in the anti-bonding molecular orbital. When the bond order increases, stability also increases. That means the strength of the molecule also increases. And similarly, when the bond order increases, bond length is decreases. Now, let us see the applications of molecular orbital theory for the few molecules. First one is the hydrogen molecule. In the hydrogen molecule, consider the formation of a hydrogen molecule. According to the molecular orbital theory, two atomic orbitals, one from each hydrogen atom, approach to form a molecule. The number of molecular orbitals formed from atomic orbitals is equal to the number of atomic orbitals. The molecular orbitals which lowers the energy brings out the stability in the system and is responsible for bonding between the atoms. This type of molecular orbitals are called as bonding molecular orbitals. The bonding molecular orbitals of the type which is formed from 1s atomic orbital as denoted as sigma 1s. The electron density in the bonding molecular orbitals is more in the internuclear region than at the end. The other type of molecular orbitals corresponds to higher energy status. The electron density of such molecular orbitals maximum at the end. This is known as antibonding molecular orbital. Antibonding molecular orbital denoted as asterisk mark. In a hydrogen molecule is formed from 1s2 atomic orbitals of two atoms. They give rise to two molecular orbitals, that is sigma 1s and sigma star 1s. The two electrons are filled according to the alpha principle. Thus, both these electrons goes to the lower energy bonding molecular orbital and anti-bonding molecular orbital remains vacant. That the bond order of the hydrogen atom is equal to half into number of electrons in bonding orbital minus number of electrons in the anti-bonding orbitals. So, half into 2 minus 0, that is bond order is equal to 1. That is, hydrogen molecule is bonded by one bond as hydrogen single bond hydrogen, and the hydrogen molecule has diamagnetic in nature because it does not have an unpaired electron. Its molecular orbital configuration is sigma 1s2 sigma star 1s0. Next we see the helium molecule. Let us consider the combination of two helium atoms to form a helium molecule. Each helium atom has two 1s electrons. Thus, there are 4 electrons to be accommodated. The sigma 1s molecular orbital will accommodate 2 electrons and the sigma star 1s will accommodate 2 electrons. There are 2 electrons in each of the bonding and the anti-bonding orbitals. Its molecular orbital configuration is sigma 1s2 sigma star 1s2. That is, bond order is equal to half minus half into 2 minus 2. That is 0. Bond order is 0. There is no bond between helium molecule. Or in other words, there can be no bond between the 2 helium atoms, that the helium molecule cannot exist. Next we see the molecular orbital theory for the nitrogen molecule. In the nitrogen molecule, that is, the electronic configuration of nitrogen atom is 1s2, 2s2, 2px1, 2py1, 2pz1. That is, the 7 electrons are accommodated in the Hapa principle. Each atom contributes 5 valency electrons. The molecule would have 8 molecular orbitals. 10 electrons are to be accommodated in them. 8 electrons go to the bonding molecular orbital and 2 electrons go to the antibonding molecular orbital. This gives the number of bond order half into 8 minus 2. That is, half into 6. There is bond order for the nitrogen molecule is 3. So, nitrogen molecule has a triple bond. There are 2 electrons each in sigma 2s and sigma star 2s orbitals. So, they become anti-bonding orbitals. There are 2 electrons in the sigma 2p molecular orbital and pi 2p molecular orbitals. So, there is 1 sigma bond and 2 pi bonds in a nitrogen molecule. That is a N triple bond N. Since there are no unpaired electron in the molecular orbital structure, so nitrogen molecule is diamagnetic in nature. Next we see oxygen molecule. The electronic configuration of oxygen is 8. Oxygen atom. The electronic configuration of oxygen is 1s2, 2s2, 2px2, 2py1, 2pz1. Each atom contributes 5 valency electrons, that is in a 2p orbital, that is 6 electrons. The oxygen molecule would have 8 molecular orbitals. 12 electrons are to be accommodated in them. The electrons are filled following the APA principle. 8 electrons go to the bonding orbital, 2 electrons go to the sigma star 2s anti-bonding orbital. 2 lone pair of electrons go to each of the degenerate pi star 2p y and pi star 2p z anti-bonding molecular orbital. So, bond order of the oxygen molecule is half into 8 minus 4, that is bond order for the oxygen molecule is 2, that is the double bonded compound. In the oxygen molecule, we can calculate the number of sigma orbital. Sigma orbital can be calculated using the formula half into number of electrons in a sigma orbital minus number of electrons in the sigma star orbital. So, number of sigma orbitals equal to half into 4 minus 2, that is equal to 1. That is, in your oxygen molecule contains 1 sigma bond. Now, we calculate number of pi bonds in the oxygen molecule. That is, in your formula, half into number of electrons in a pi orbital minus number of electrons in a pi star orbital. So, number of pi bond is equal to half into 4 minus 2 is equal to 1. There is 1 pi bond. So, in your oxygen molecule, that is in your 1 sigma bond and 1 pi bond. That is oxygen double bond, the oxygen atom, double bond oxygen atom. Since there are 2 unpaired electrons in a 2 degenerate 2 pi star orbitals. So, oxygen molecule is paramagnetic in nature. The difference between the number of bonding electrons and anti-bonding electrons determines the tightness of the bonding. In oxygen molecule, this difference is 4. Hence, its binding energy is more. Correspondingly, dissociation energy is also high in the oxygen molecule. Now, let us see the O2 negative ion, oxygen molecule minus ion for a molecular orbital diagram. This oxygen negative ion has oxygen atom and 1 oxygen negative ion. The electronic configurations are 1s2, 2s2, 2p4 for oxygen atom, and the oxygen negative ion configuration is 1s2, 2s2, 2p5. Thus, we have 6 plus 7, 13 electrons in their valency shell. So, its molecular electronic configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p4, pi star 2p3. Now, we calculate the bond order of the oxygen molecule negative ion. That is half into 8 minus 5, bond order is equal to 1.5. In an oxygen molecule, positive ion. In this ion has oxygen atom and 1 oxygen positive ion. Their electronic configurations are 1s2, 2s2, 2p4 and 1s2, 2s2, 2p3 respectively. Thus, they have 6 plus 5, 11 electrons in their valency shell. So, its molecular electronic configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p4, pi star 2p1. So, bond order of the oxygen positive ion is equal to half into 8 minus 3, that is equal to 2.5. In your oxygen molecule, bond order is 2, oxygen negative ion bond order is 1.5, oxygen positive ion bond order is 2.5. In this module, we know about what is the molecular orbital theory and what is the bonding molecular orbital and anti-bonding molecular orbital. We see some of the applications for the molecular orbital diagram. In the next module, we see the another applications of the molecular orbital theory and the hydrogen bonding. Thank you.